Let's get started by looking at how we use linear algebra to represent sets of linear equations. This slide here shows a set of two linear equations, these two, with two unknown variables, x1 and x2. Now you may remember how to solve equations like this, that is, how to find the x1 and x2 values that satisfy these set of equations. The basic way of doing it is you multiply one of these rows, one of these equations, by some number such that it cancels out with another one. So here we could take the second row and multiply it by 2 to get negative 4x1 plus 6x2 equals 18. Then we're going to add it to the first equation, and the x1 terms cancel out. So what we're left with here is just x2 equals 5. I'll write that over here as the solution we have, x2 equals 5. And then we substitute the solution back into the first equation, or the second equation, it could be either one, to have, in this case, 4x1 minus 25 equals negative 13. So that means 4x1 equals 8, or x1 equals 2. That is the solution that satisfies this set of linear equations here. Now, when you have two equations and two unknowns, it's not that hard to do these kind of manipulations by hand and just write them out explicitly. But we can represent these equations much more compactly using matrix notation. We can write these equations as AX equals B, with A and B defined as follows. The rows of the matrix A correspond to the coefficients in these equations, and the B vector corresponds to the elements on the right-hand side. The X vector is just a vector containing the two unknown elements here. Now, as you might imagine, when you only have two variables and two equations, it's pretty easy to write it out, as I said. But when you have 1,000 variables or 1,000 different equations, it can be very cumbersome to write these terms out equation by equation. And so the notation of linear algebra really helps us describe these large sets of linear equations very compactly.